This presentation is delivered by the Stanford Center for Professional Development.
Hey there, good afternoon. Welcome to Monday. Today's a big day, right? We've got a couple of recursive backtracking examples that we didn't get to on Friday that I'm going to talk you through today. And then we're going to talk a little bit about pointers, the long anticipated introduction to the one of the scarier parts of the C++ language as a kind of a step tone toward building linked lists and the recursive data idea that we will study today and continue into Wednesday. So the two examples I want to do are both based on the same backtracking pseudocode that we were using on Friday, and I just want to go through them. I'm going to do a little bit less attention to the code and a little bit more attention to the problem solving, because at some point I think the problem solving is really where the tricky stuff comes in, and then the kind of turning it into code, there's some details there, but they're not actually as important, so I'm going to de-emphasize that just a little bit here and think more about solving it. So this is the pseudocode for any form of a backtracker, right, that has some sort of, failure and success cases, like when we've run out of choices, we've hit a dead end or we've hit a goal state, there's no more decisions to make, right? Is this where we want to be, yes or no? And then otherwise there's some decisions to make, and for all the possible decisions we could make, we're going to try one, be optimistic about it working out, make that recursive call that says that choice was where I wanted to be. If it returns true, or whatever the success return value is, then we return true. Right? No need to look any further. That choice was good enough. If it didn't work, then we're going to unmake, try some other choices. If we try all the things available to us and no case, right, did solve ever return true, then we can only conclude that the configuration as given to this call was unsolvable, which is what that return false causes it to back up to some earlier call and start unmaking that next layer of decisions, and then recur further down, eventually either unwinding the entire recursive stack all the way back to the beginning and saying it was totally unsolvable no matter what, or eventually finding some sequence of decisions that will lead to one that will get us to a success case. So what I'm going to show you here is the Sudoku, which is those little puzzles that show up in newspapers everywhere. They're actually not attributed to apparently to the Japanese, but apparently got a lot more popular under its Japanese name than it did under the original English name for it. And the goal of a Sudoku, if you have never done one, right, is it's a 9x9 grid in which you're trying to place numbers, and the requirement for the numbers is such that within any particular row or any particular column or any particular block, which is a 3x3 subsection of that, the numbers 1 through 9 each appear once. So you can never have more than 2 1s in a row, 2 2s in a column, 3 3s in a block, or anything like that. And so there has to be some rearrangement, or in fact permutation, of the numbers 1 through 9 in each row, in each column, in each block, such that the whole puzzle kind of works out logically. So when it's given to you, usually some fraction of the slots are already filled in, and the goal for you is to fill in those remaining slots without violating any of these rules. Now, the sort of pure Sudoku solvers don't really use guessing. It's considered actually poor form. That you're supposed to actually logically work it out by constraints about what has to be true here versus what has to be true there to kind of realize that what choices you have. We're actually not going to be a pure artistic, Sudoku solver. What we're going to do is we're actually going to use a brute force recursive algorithm that's just going to try recursive backtracking, which is to say, make an assignment, be optimistic about it, and if it works out, great, and if not, we'll eventually come back to that decision and revisit it. So what we have here basically is a big decision problem. Of the 81 squares on here, about 50 of them, right, need to be chosen. For each of those 50 squares, right, we're going to do them one at a time and recur on the remaining one. So, choose one. Maybe we'll just go left to right from the top. Choose that one at the top. Make an assignment that works. And so at that point, we'll use the context we have in the problem here. So, for example, if you look at this first row, there's a 1 in this column, so we can't use 1. There's a 2 in that block, so we can't use 2. But there's not a 3 in either that row or that column or that block, so we say, well, 3 looks good, just trying the numbers in order. We'll be optimistic, say that works, and say, well, if we planted a 3 here, could we recursively solve the remaining 49 holes and work it out? And so when we get to that next one, we're looking at this one and saying, okay, well, we could put a 1 here, right? Because there's not a 1 in this column, not a 1 in that row, not a 1 in that block. So we'll kind of move on. I'm going to do a little demo of that for you. And the idea is to kind of keep moving our way across, and only when we get to a dead end, based on some of our earlier decisions, will we unmake and come back. So let me Okay, so that's the same set of numbers there. So I put the 3 up in the corner. And so it puts the 1 here, thinking, okay, that looks good. So it gets to the next square over here, and then the 1 can't be used because it's actually already in use both in that column and in the row we're building so far, but 2 can be used. 2 doesn't conflict with anything we have so far. And so it just keeps going optimistically, right? At that stage over there, it turns out almost all the numbers in use. There's most of the numbers all the way up through 7 and 9 are there, and 7's in its column. So in fact, the only number that could possibly be is 9. So the only choice we have here to try is 9. And then we'll place the 7 next to it. And so now we have a whole row that doesn't conflict with any of its blocks and this thing, and then we just keep moving on, right? So that is to keep kind of going from top to bottom, left to right. We'll place that 4, place another 1, place a 3. So it's actually choosing them, it's actually going in order from 1 to 9, just picking the first one that fits, right? So when we get to the next square here, right, it can't use 1, it can't use 2, it can't use 3, it can't use 4, it can't use 5 because they're all in that row. It can't use 6 because it's in the column. It can't use 7 because it's in that row, but it should be able to use 8, and so it'll place an 8 there. So it just kind of examines them in sequence until it finds the first one that doesn't violate anything's already decided, and then kind of moves optimistically forward. So about this point, right, we're doing pretty well, but we're starting to run into some troubles. If you look at the next one over here, it'll place the 6 there, but then it will once the 6 is placed there, then it looks to the right and it says, oh, I need to put a 9 there. That's the only number left. It tries all the numbers 1, 2, 3, 4, and it says, that ain't going to work. And so it actually fails on the rightmost column, which causes it to back up to the one right before it and say, well, why don't you try something else here? Well, it looks at 7, 8, and 9. None of those can work either, so it's actually going to back up even further. And say, well, what if we try to put a 9 here? That also doesn't work. So now it's going to start seeing that it's kind of unwinding as the constraints we have made have kind of got us down a dead end, and it's slowly working its way back out to where the original bad decision was made. So it tries again on moving 9 in here and moving across, right? But again, kind of working its way forward, but then kind of backing its way up. And let me go ahead and just run it faster so you can kind of see it. That it's working on that row for a while, but it's interesting to note that the top row stays relatively constant. It kind of believes that, well, that first 3 must have been good because we're getting somewhere on that, and it keeps kind of going. And you can see that the activity is kind of always at the kind of tail end of that decision making, which eventually, right, worked its way out. And so it turns out, right, those 3 1s that we did put in the first slots were fine. That as choices, right, it did work out. We didn't know that when we started, right, but it was optimistic, right? It put it down and then it kept moving, and then eventually, right, worked out how the other things that had to get placed to make the whole puzzle be solvable. And so this thing can solve actually any solvable Sudoku, right, and if it's not animating, and instantaneously, even though it is really doing it in a fairly crude way, right? It's basically just trying everything it can, moving forward, and only when it kind of reaches a contradiction based on some of those choices and say, well, that can't possibly be because at this point I'm forced into a situation where there's nothing that works in the square. So it must be that some earlier decision was wrong. And you notice that when it backs up to the most immediate decision. So if you think of it in terms of recursive call, here's your first decision, your second decision, your third decision, your fourth decision, your fifth decision. If you get down here and you're like trying to make your 8th decision, and there's nothing that works, right, the decision that you come back to will be your 7th one, the one right before it. You don't go throw everything away and start over. You don't go all the way back to the beginning and say, oh, well, that didn't work. Let's try again. It's that you actually use the kind of context to say, well, the last decision I made was probably the one that needs a little fixing. Let me just back right up to that one. And that's the way the calls unwind. And it says, well, pick up trying some other options there. Which ones have we not tried on that one? And then go forward again. And again, if you get down to that 8th decision and you're still stuck, you come back to the 7th decision again. And only after kind of the 7th decision has gone back and forth with the 8 unsuccessfully through all its options would we eventually return to that 6th decision and potentially back to the 5th and 4th and so on. The code for this guy, a little bit abstracted, that should very much fit the pattern of what you think recursive backtracking looks like, and then the kind of sort of goopier parts that are about, well, what does it mean to test a Sudoku for being assigned and having conflicts has actually been passed out into these helper functions that manage the more domain-specific parts of the problem. So at the very beginning, it's like find an unassigned location in the grid, and it returns the row and column by reference. It turns out in this case those are reference parameters. So it basically just searches from top to bottom to find the first slot that actually does not have a value currently in it. If it never finds one, so it exhaustively searched the grid and didn't find one, then it must be that we have a working Sudoku, because we never put a number in unless it worked for us. And so if we've managed to assign them all, we're done. If this didn't return true, that meant it found one and it assigned them in row and column. And then what we're going to go through the process of is assigning that row and column. So we look at the numbers 1 through 9. If there are no conflicts for that number, so it doesn't conflict with the row, column, or block, that number isn't already in use in one of those places, then we go ahead and make the assignment. And then we see if we can solve it from here. So having updated the grid to show that new number is in play, if we move on, the next call to solve Sudoku will then do a search for find unassigned location. This time the one that we previously found has been assigned, so it actually won't get triggered on that one. It'll look past it further down into the puzzle, and eventually either find the next one to make a call on and kind of work its way through, or to have solved the whole thing. If it didn't work, so we made that assignment to the number 9, and we went to solve, and eventually this tried all its possibilities from here and nothing came up good, then this unassigned constant is used to unmake that decision and come back around and try assigning it a different number. If we try all of our options, so for example, if we never find one that doesn't already conflict, or if we try each one and it comes back false, right, that this return false here is what's triggering the backtracking up to the previous recursive call to reconsider some earlier decision, the most recent early decision before this one, and say that was really our mistake, right? We got to unmake that one. So it should look like kind of all the recursive backtracking all sort of looks the same, right? If we're at the end, here's our base cases for all our options. If we can make this choice, make it, try to solve it, be optimistic. If it works out, return. Otherwise, unmake it, allow the loop to iterate a few more times, trying again. If all of those things fail to find a solution, then that return false here causes the backtracking out of this decision. Unassigned is just some constant. I made up, I used -1, in fact, just to know that it has no contents. So just specific to Sudoku in this case. Now would be a great time to ask a question. You guys kind of have that sort of half okay look on your face. It could be I'm totally bored. It could be I'm totally lost.
Where do row and column get assigned?
So they find unassigned location takes row and column by reference. So if you look, the full code for this is actually in the handout I gave out last time, and so they're just passed by reference into that function. It returns true if it assigned them something, and then they have the coordinates of that unassigned location. Question over here.
How'd you know to write solve Sudoku as a bool rather than as like a void function?
Well, in this case, that's a great question, right? In most cases in the recursive backtracking, I am trying to discover the success or failure of an operation, and so that's a good way to tell, because otherwise I need to know, did it work? And so if I made it void, then there have to be some other way I figured it out. Maybe, that you have to check the grid when you're done and see that it no longer has any unassigned locations, but the bool is actually just the easiest way to get that information out. So typically your recursive backtracking routine will probably return something. Often it's a true or false. It could be, in some other case, just some other good known value and some other sentinel that says, bad value. So for example, in the finding an anagram of the words, it might be that it returned the word if it found one, or returned an empty string if it didn't. So using some sort of state that says, here's how, if you made the call, you'll know whether it worked. Because we really do need to know, make the call and find out whether it worked. Well, how are we going to find out? One of the best ways to get that information is from a return value. Way in the back.
How exactly does the return false trigger the backtracking?
So think about this is that, it's hard to think about because you have to kind of have kind of both sides of the recursion in your head. But when, let's say we're on the fifth decision, right? We make the call to solve the Sudoku that's going to look at the sixth decision, right? If the sixth decision fails, it says, I looked at all my choices and none of them worked, right? It's that causes the fifth decision to say, well, go solve for the sixth decision down. Well, the sixth decision came back with a false. It got to this case after trying all its options. Then it's the fifth decision that then says, okay, well, then I better unmake the decision I made and try it again. And so at any given stage, you can think about the caller and the callee. It's saying, I'm making a decision. You tell me if you can make it work from here. If the delegate that you passed on the smaller form of the recursive problem comes back with a return false, it meant I tried everything I could possibly do, but there was no way. The situation you gave me was unworkable. And that says, oh, okay, well, you know what? It must have been my fault, right? I put the wrong number in my box. Let me try a different number, and now you try again. And so they're constantly kind of these, you have to keep active in your mind the idea that there's this whole chain of these things being stacked up, each of them being optimistic and then delegating down. And if your delegate comes back with there was nothing I could do, then you have to revisit your earlier optimistic decision, unmake it, and try again. And so that this is the return false that to the outer call, the one that made this solve call, unwinds from. Somebody over here.
Can you solve any recursive problem using this?
Pretty much any recursive piece of thing can be reformed into a backtracking form, right? You need to do a little bit of like the machination we tried last time about, well, take a void returning thing and make it return some true or false, and there's kind of like make a decision and be optimistic, see if it worked out. But that kind of rearrangement of the code should work with pretty much all your standard recursion stuff. So any kind of puzzle that actually, like all these kind of jumble puzzles and crossword puzzles and things that involve kind of choosing, right, can be solved with recursive backtracking. It's not necessarily the fastest, right, way to get to a solution, but it will exhaustively try all the options until a sequence of decisions, right, leads you to a goal if there is a goal to be found. And so that if you can think of your problem as a decision problem, I need to make some decisions and then from there make some more decisions and so on, and eventually, right, I will bottom out either at a goal or a dead end, then you can write a recursive problem solving backtracker to solve it. Way in the back.
This doesn't have anything to do with recursion, but how did you slow down your simulations?
How did I slow it down? I'm just using pause. There's a pause function in our extended graphics library, and you just give it a time. You say 1 second, half a second, and just I use that a lot in our demos, for example, for the maze, so that you can actually see what's going on. That way it just animates a little more. It's extended graphics, ext graph.h. Let me show you one more. Kind of just in the same theme, the idea of taking sort of some puzzle that somebody might give you, trying to cast it in terms of a decision problem, right, where you make decisions and then you move on. Can I solve something like these little cryptarithmic puzzles? So here's send plus more equals money. I've got 8 digits in there, 8 letters in there, D-E-M-N-O-R-S-Y across all of them. And the goal of this puzzle is to assign these letters, 8 letters, to the digits 0 through 9 without replacement, so that if D is assigned to 3, it's assigned to 3 in all places. For example, O shows up 2 places in the puzzle. Both of those are either a 2 or both are 3. There's not one that's 1 and one that's another. And each digit is used once. So if I assigned 2 to O, then I will not assign 2 to D. So what we've got here is 8 letters. We've got 10 digits. We want to make an assignment. What we've got here is some choices. The choices are, for each letter, what digit are we going to map it to? Another way to think about it is if you took these 8 letters and then you attached 2 dashes on the end, and then you considered that the letter's position in the string was the index of it was its digit, it's really just like trying the permutations, right? Rearranging those 10 letters in any of those sequences. So right now, for example, maybe D is assigned 0 and 1 and 2 and so on, and these guys are 8 and 9. Well, if you rearrange the letters into some other permutation, then you've made a different assignment. So in effect, right, what you're looking at is a problem that has a lot in common with permutations, right? I'm going to make an assignment, take a letter off, decide what index it's going to be placed at. So it's kind of like deciding where it would go in the permutation. And then that leaves us with a smaller form of the problem, which has 1 fewer letters to be assigned. And then recursively explore the options from there to see if we can make something that makes the addition add up correctly, that D plus E equals Y means that if D was assigned 5 and E was 3, then Y better be 8 for this to work out. So the first form I'm going to show you is actually just the dumb, exhaustive, recursive backtracking that works very much like the Sudoku problem, where it finds the next unassigned letter, it assigns it a digit of the next unassigned digits, right, and then just optimistically figures that'll work out. After it makes an assignment for all the letters, it says, take the puzzle, convert all the letters into their digit equivalents, and see if it adds together correctly. If so, we're done. If not, then let's backtrack. So I'll show you the code first, because it's actually quite easy to take a look at. Again, it has helper routines that kind of try to abstract the pieces of the puzzle that actually aren't very interesting from kind of looking at just the core of the recursive algorithm. So it looks a lot like Sudoku in that if letters do assign, so it actually keeps this string of the letters that haven't yet been assigned, If there are no more letters in that string, we take one off at each time we assign it. Then we check and see if the puzzle is solved. So that kind of does the substitution and does the math and comes back saying yes or no. If it worked out, we'll get a true. If it didn't work out, we get a false. If we still have letters to assign, then it goes through the process of making a choice. And that choice is looking at the digits 0 through 9. If we can assign it, so looking at that first letter and that digit, and then that's making sure that we don't already have an assignment for that letter, that we don't have an assignment for that digit, sort of make sure that just the constraints of the problem are being met. If we're able to make that assignment, then we go ahead and make a recursive call, having one fewer letters to just make a decision for, and if that worked out, true. Otherwise, we do an unassignment and come back around in that loop. And then eventually the same return false at the bottom, which said, well, given the previous assignments of the letters before we got to this call, there was nothing I could do from here to make this work out. So let me show you this guy working, because you're going to see that it is actually a crazy way to try to solve this problem in terms of what you know about stuff. So I say CS plus U equals fun, a well-known equation. Okay. So I did this little animation that's trying to get you to visualize what's going on at any given stage. So it has the letters down across the bottom, S, U, N, C, O, Y, F. That's the string of letters to assign. It's going to assign it the next available digit when it makes that recursive call. So the first recursive call is going to be about assigning S, and then the next call will be then assign U, and the next call and so on. So it always gets up to 7 deep on any particular thing. And so it says, okay, well, first digit available is 0. Go ahead and assign that to S. So it's going to make a call there. And then it says, okay, well, look at U. Well, we can't use 0 because 0 is already in use. Well, why don't we assign U to be 1? Okay, sounds good. Keep going. And that'll say, okay, let's get to N. Let's make an assignment for N. It says, oh, look around. Okay, well, 0's in use, 1's in use. How about 2? Okay, good. And then it assigns this to 3, this to 4, this to 5, and this to 6. Okay, it gets to here and it says, hey, does that work? 30 plus 541 equals 612. No. Okay, well, you know what the problem was? It was F, right? I assigned F to 6. How stupid of me. It can't be 6. Let's make it 7. And then it says, oh no, oh, I'm sorry. 30 plus 541, that's not 712. Oh, how silly. I need to assign F to be 8. And it's going to do this for a little while. A long while for that. And then it says, oh, okay, well, you know what? Given the letters you'd assigned to the first 6 things, when you got to F, I tried everything I could, and there was nothing I could do to fix this. So you know what the problem was? It's not me. It's not me. I'm not the problem. You're the problem. So it returns false from this call at the bottom, having tried all its options, which causes Y to say, oh, yeah, I know I said 5. Did I say 5? I didn't mean to say 5. I meant to say 6. And so it moves up to the 6 option. Again, optimistically saying, that's good, go for it, see what you can do. So it picks 5, that won't work, right? Picks 7. It's going to do this for a long time, right? Because it turns out, right, this is one of those cases where that very first decision, that was one of your problems, right? If you assign S to be 0, there's nothing you can assign U and N to be that are going to work out. So what it's going to be going through is this process, though, of having committed to this early decision and kind of moving on. It's going to try every other variation over here before it gives up on that. So let me set it to going. Even though CS plus U does equal fun, I guarantee it. We'll let it do some work for a while. So those bars as they grow up are desperation. You can think of that. It's like it's running out of options. It's running out of time, and it's like, oh, wait, earlier, back up. And so you can kind of see how far it's backed up by sort of how tall some of the deeper recursive calls, right, the earlier ones in the sequence. And so it hasn't, revisited any of these decisions because it's really busy over here. But you can see that C is now up to 7. It'll get up to 8. It'll get up to 9. And that was when it will cause itself to say, I tried everything that was possible from C on down, and there was no way to make this thing work out. It must be that the bad decision was made earlier. Let's back up and look at that. And so it'll come back to the decision N, bump it up by 1, and then go again. It's going to do this a long time, right? Go through all the options for N and its neighbors before it comes back and revisits the U. It's going to have to get U all the way up right through, having tried 1, 2, 3, 4. So adding 0 to 1 and 2 and 3 and 4 and discovering it can never make a match over there before it will eventually decide that the S was really where we we got ourselves in trouble. So this is kind of in its most naive form, right? The recursive backtracking is doing basically permutations, right? You can see this as actually just permuting the digits as they are assigned to the numbers. And there are, in this case, 7 factorial different ways that we can make this assignment. And there are a lot of them that are wrong, right? It's not being at all clever about how to pick and choose among which to explore. So in its most naive form, right, recursive backtracking can be very expensive because often you're looking at things that have very high branching and very long depth to them, which can add up to a lot of different things tried. Just using some simple, in this case, heuristics, sort of information about the domain, can help you to guide your choices instead of just making the choices in order, trying the numbers 0 through 9 as though they're equally likely, or kind of waiting to make all the assignments before you look at anything to see if it's actually good. There's actually some ways we can kind of shape our decision making to look at the most likely options before we look at these more, first finding the problem instead of niggling around this dead end. So I'm going to let that guy work for a little bit while I show you another slide over here. So what the smarter solver does is that it doesn't really consider all permutations equally plausible. We're going to use a little grade school addition knowledge. If I look at the rightmost column, the least significant digit, I'm going to assign D first. I assign D to 0. I assign E to 1, and then I look at Y. I don't try Y is 5 or 7 or anything like that. I say there's exactly one thing Y has to be, right? If D is 0 and E is 1, then Y has to be 1. And I can say, well, that won't work because I already used 1 for E. So it'll say, well, that's impossible. Something must be wrong early. Rather than keep going on this kind of dumb dead end, is to realize right away that one of the decisions I've already made, D and E, has got to be wrong. So it'll back up to E, and it'll try 2, 3, 4, very quickly realizing that of all the things you could assign to E, once you have assigned D to 0, you're in trouble. And so it'll quickly unmake that decision about D and work its way down. So using the kind of structure of the problem. So it means there's a little bit more housekeeping about where I'm at and what I'm doing and what's going on, but it is using some real smarts about what part of the tree to explore rather than letting it kind of just go willy-nilly across the whole thing. So let me get that out of the way. And I'll run this one. I say CS plus U equals fun. Okay. So it goes 0 here. It tries the 1. And it says, no, that won't work. How about the 2? No, that won't work, right? Because there's nothing you can assign the n that'll make this work. And so it immediately is kind of failing on this. And even after it tries kind of all 9 of these, it says, no, none of these are looking good. Then it comes back to this decision and says, no, actually S of 0, that wasn't so hot. How about we try S as 1? And then kind of works its way further down. Hello? Okay, so let me try this again. Let me get it to just go. Okay. So it took 30 assignments, 30 different things it tried before it was able to come up with 41 plus 582 equals 623, which does add correctly. It didn't have to unmake once it decided that S was 1. It turns out that was a workable solution, so it didn't have to go very far once it made that commitment, and then you can see it kind of working its way up. So 30 assignments, right, across this tree that has, hundreds of thousands, 7 factorial, a very large number, but very quickly kind of pruning down those things that aren't worth looking at, and so focusing its attention on those things that are more likely to work out using information about the problem. It doesn't really change what the recursion does. It's kind of interesting to think that the same backtracking and recursive strategy is the same in all these problems, but what you're trying to do is pick your options, like looking at the choices you have and trying to decide what are the more likely ones, which ones are not worth trying, right? So sort of directing your decision making from the standpoint of trying to make sure you don't violate constraints that later will come back to bite you and things like that. This one's back here. It's at 13,000. And working hard, getting desperate, doing its thing. Still has not unmade the decision about S is 0, so you can get an idea of how much longer it's going to take. We'll just let it keep going. I'm in no hurry. And let it do its thing. So let me, before I move away from talking about recursion, just try to get you thinking just a little bit about how the patterns we're seeing, right, are more alike than they are different. That solving a Sudoku, solving the 8 queens, solving the find an anagram in a sequence of letters, that they all have this general idea of there being these decisions that you're making, and you're working your way down to where there's a fewer and fewer of those decisions until eventually you end up sort of, okay, I'm done. I've made all the decisions I can. What letter goes next, or whether something goes in or out. And that the two problems that I call the kind of master or mother problems, right, of permutations and subsets are kind of fundamental to adapting them to these other domains. And so I'm going to give you a couple examples of some things that come up that actually are just kind of permutations or subsets or some variation of them. You can help me think about it a little bit. One that the CS people are fond of is this idea of knapsack filling. It's often cast as someone breaking into your house. We're all criminals at heart, apparently, in computer science. And you've got this sack, and you can put 50 pounds of stuff in it, right? And you're looking around, at all the stuff that's up for grabs in this house that you've broken into. And you want to try to pack your sack, right, so that you've got 50 pounds of the high-value stuff. So let's say there's like 100 things, right, you could pick up, right, and they weigh different amounts, and they're worth different amounts. What's a strategy for going about finding the optimal combination of things to stick into your sack, right, so that you got the maximum value from your heist? What problem does that look like that you've seen? It's a subset. It's a subset. You're saying, is it in or out? Right? So if you look at the, the Wii and you say, oh, should I take the Wii? It weighs this much and it's this much value. Well, let's try it in and see what happens, right? And see what else I can stuff in the sack with that, right? And then see how well that works out. I should also try it with it out. So while you're standing there trying to decide what to steal, you have to type in all the values of things and have your computer program go through the kind of machinations of, we'll try this with that, because some things are big but have a lot of value, but they only leave a little bit of odd space left over you might not be able to use well or something. But what you're looking for is the optimal combination, the optimal subset. So trying the different subsets tells you how much value and weight you can get in a combination, and then you're looking for that best value you can get. You're the traveling salesman. You've got 10 cities to visit. Boston, New York, Phoenix, Minneapolis, right? You want to cover them in such a way that you spend the minimum amount of time, in painful air travel across the U.S. Well, you certainly don't want to be going Boston, New York, right? Like Boston to L.A. to New York to Seattle to D.C. to Los Angeles, back and forth, right? There's got to be a pattern where you kind of visit the close cities and work your way to the far cities to kind of minimize your total distance overall. What problem is that really in disguise? You got 10 cities? What are you trying to do? Help me out. I hear it almost louder. Permutations. You got a permutation problem there, right? You got 10 cities. They all have to show up, right? And it's a permutation. Where do you start? Where do you end? Where do you go in the middle, right? What sequencing, right, do you need to take? So what you're looking at is, try the permutations. Tell me which ones come up short. There are things read about heuristics that can help this, right? The idea that certainly like the ones that are closer to you are likely to make a better choice than the longer ones. So kind of using some information about the problem can help you decide which ones are more promising avenues to explore. But in the end, it's a permutation problem. I'm trying to divide you guys into fair teams. I want to, divide you up into 10 teams to have a kind of head-to-head programming competition. I happen to know all your IQs. I don't know, some other useless fact that perhaps we could use as some judge of your worth. And I want to make sure that each team has kind of a fair amount of IQ power in it relative to the others, so that I didn't put all the superstars on one team. What am I doing? Trying to divide you guys up? It's a subset problem, right? It's in this case, it's a subset that's not just in or out. It's like, which team am I going to put you in? So I've got 10 subsets to build. But in the end, it's an in-out problem that looks like, well, I have the next student. Which of the 10 teams can I try them in? I could try them in each of them, right? So in some sense, it's try them in the first team, the second team, the third team, right? And then pull the next student, try them in those teams, and then see whether I can come up with something that appears to get a balanced ratio when I'm done. It turns out you can take the letters from Richard Milhouse Dixon and you can extract and rearrange them to spell the word criminal. I am making no conclusion about anything having done that, just an observation of fact. But that sort of process, right, of trying to find, well, what is the longest word that you can extract from a sequence of letters? What kind of things is it using? Anything you've seen before? What was somebody come on. I hear the whispering, but no one wants to just stand up and be committed. How about a little both, right? The what? A little bit like the Sudoku, right? It's got a permutation sort of backing. It's also got a little bit of a subset backing, right? The idea is that I'm not choosing all the letters from this. So in fact, there's a subset process, which is deciding whether it's in or out. And then there's a permutation problem, which is actually rearranging them, right? That picking the C and the R and the I and the M and then kind of rearranging them. So in fact, it has kind of a little bit of both, right? Which is what sequence of letters can I extract and then rearrange to make a word. Would end up using kind of elements of both of those kinds of recursion sort of mixed together. So that when you look at a lot of recursion problems, they end up actually just mapping down to one or the other, or maybe a little bit of both. And so feeling very comfortable with those problems, how you turn them into a recursive backtracker, and how you can recognize, right, their roots inside these other problems is kind of a really good first step to becoming kind of a journeyman in the way of recursion. So just whenever you see a new problem, you start thinking, okay, is it permutations, is it subset, or is it something totally new? It's probably much more likely to be the first two than the third, and so try to use the ones that you feel really comfortable with to kind of branch out to solve similar problems, right, where the domain is a little different, but the structure of the code is still very much the same. All right, I've got 10 minutes to teach you about pointers. It should be no problem. Let's go see what that guy back there is doing. Oh, look at that. 38,000 assignments, still has not given up on that S is 0. He's a trooper. Okay. All right. So this is definitely going to be your first introduction on kind of the first day of talking about this. This is not the only day, so don't get too worried about me trying to do it in 10 minutes. What I'm going to do is give you the kind of a little bit of the basics today, and we're going to follow up with some more stuff tomorrow where we start kind of making use of them and doing something kind of interesting with them. So there is this notion in C++, which is inherited from the C language, in fact, of using a variable type called a pointer as part of the things that you operate on. Okay. People tend to have a lot of trepidation. Just the word pointer causes a little bit of fear, kind of, to immediately rise in a new programmer. But hopefully we can demystify a little bit and then also get a little bit of understanding of why there are reasons to be a little bit wary of working with pointers. A pointer is actually an address. So here's a couple things we have to kind of think about a little bit how the machine works to have a vision of what's going on here. That when you declare variables, here I am in main, and I declare, int num and string s, that there is space set aside as part of the working memory of this program that is going to record whatever I assign to num or s. So if I say num equals 45 or that s equals hello, that there has to be memory that's being used to hold on to that. And as you declare variables, right, more of this space is set aside. And when you initialize it, when you read to it, when you write to it, right, that space is being accessed and updated as you go through. When you open a new scope, right, new variables come into scope. When you close that scope or leave that function, that space gets deallocated. Kind of all this happens on your behalf without you actually taking a really active role in it. But in fact, you do have to have a little bit of understanding of that to kind of get the idea of what a pointer is about. Is that there is this just big sequence of data, starting from an address 0. You can think of these things as actually having a little number on them. So maybe this is number 1000, and this is number 1004. In this case, assuming that we're numbering by the byte, which is the smallest chunk of memory we can talk about, and that an integer requires 4 of those bytes to store all the different patterns for different kinds of numbers, so that the bytes from 1000 to 1003 are reserved for holding on to the information about 45, and then from 1004 to however big a string is, which we don't even really know how big that is, so we'll kind of leave it a little bit vague here, is going to be set aside for storing the information about that string. Okay. So usually it's of interest to the compiler writer to know where things are being stored and what's going on. But it also turns out to be somewhat useful for us to be able to talk about something by address. Instead of saying the variable whose name is num, I can talk about the variable who lives at location 1000. You can say there is an integer, and I can point to it or refer to it by saying, go look at memory address 1000 and read or write the contents there that are of integer type. Okay, It seems a little bit odd at first. You're like, well, I already have other ways to get to num. Why is it I'd want to go out of my way to find another different mechanism that can get me access to that same variable? And we're going to see that actually there's a lot of flexibility that is being bought by us adding this to our feature set, where you can say, well, I could actually have one copy of something. So imagine that you have a system like an access system where you have student records and they're enrolled in a bunch of different courses. That you're enrolled in 4 or 5 different courses, that when it comes time for a class to know who's in their list, it might be handy for them, instead of actually having a copy of that student's information, to have a pointer to one student record and have a lot of different places where there are additional pointers taken out to that same location and says, go look at the student who's at address 1000. I have the students at address 1000, at 1026, at 1035, whatever those places are, and that's one way I can talk about what students I have, and those same student addresses might show up in someone else's class list in Math 51 or Physics 43 or whatever, and that we are all referring to one copy of the student data without duplicating it. So this idea of being able to refer to stuff not just by name but by where it lives is going to give us some flexibility in terms of how we build things out of that. So let me kind of show you a little bit of the basic operations, and I'll talk a little bit along the way about this thing about why they're scary, because using memory access as your way to get to some things is a little bit more error prone and a little bit harder to deal with than some of the more other operations we have. So what I'm going to show you here is a little piece of code that shows some simple use of pointers. All right, so I'm going to draw some of the variables that are going on here. This is main, and it declares an integer whose name is num. So I'll draw a box for that. And it declares 2 pointer variables. So the addition of the asterisk by the name there says that P and Q are pointers to integers. So P and Q themselves are variables that live in the stack. So all the local variables we say live in the stack. They are automatically allocated and deallocated. When you enter a routine, the space for them comes into being. When you leave it, it goes away. And that P and Q are designed not to hold integers themselves. They don't hold numbers, but they hold the address of a number somewhere else. And so the first thing I did with P there was to assign it the address of a new integer variable that came out of the heap. So the new operator is like the new operator in Java. It takes the thing you want to create one of, it makes one of those in the heap, and it returns to you its address. And that way it works exactly like in Java. So in fact, Java actually has pointers, despite what anybody ever told you, that the way you create objects and you use new to access them and stuff like that is exactly the same as it is in C++, and it is pointers behind the scene. So I say P gets the value of a new integer. This memory over here is called the heap. So this is not to confuse you with the idea of the stack ADT we've been using, the stack class, but it helps you to remember that the stack actually kind of like by virtue of the way function calls get made, main calls A, which calls B, which calls C, that memory actually kind of is laid out like a stack. The heap is just this unordered, crazy pile of stuff. I asked for new integer, so this might be address 1000, this might be address 1004, this might be address 1008. Typically, the stack variables are laid out right next to each other. This could be like address 32,016 or something over here, some other large address. So I've assigned P to be that thing. So what actually got written into P's box is behind the scenes, there really is the number, the address 32,016, but I'm going to draw it as an arrow to remind myself that what it is it's a location of an integer stored elsewhere. The dereference operator, which is the first thing we see on this next line, says to follow P and assign it a 10. So this is taking that address that's in P, using it as a location to go look up something, and it says, and go right to that location in address 3216, the number 10. Then I said Q equals new int. So Q gets an int in the head, and maybe this is at 23,496, some other place out there. And so that's actually kind of what's being stored here, 23,496. And then I did this thing where I assigned from dereferencing P to get an integer and assign that onto what Q is. So that's the effect of kind of following P, reading its 10, and then writing it over here. So copying the integers at the end of those two pointers to make them point to the same value. So they point to two different locations, but those locations hold the same integer value. That is different than the next line without the stars, where I said Q equals P. Without the stars on it, it's saying take the address that's in P and assign it to Q, causing Q and P now to be aliases for the same location. So now I have two different ways of getting to that same piece of memory, either by reaching through P and dereferencing or reaching through Q and dereferencing it. Both of them are reading and writing to that same location in the heap where the 10 is. And then this one down here is no longer accessible. I sort of lost track of it when I overwrote Q with the copy of P. When I am done in C++, it is my job to delete things that are coming out of the heap. Yes, it should. I should update that while I'm at it, 32.016. Whereas in Java, when you say new and then you stop using something, it figures it out and it does what's called garbage collection to kind of clean up behind you. In C++, things that you knew out of the heap are your responsibility to delete. So you delete something when you're done with it. If I'm no longer using this new integer I created in the heap, I say to delete P to allow that memory to be reclaimed. And so that causes this piece of memory to get marked as freed or reusable so that a subsequent new call can have that space again and use it for things. I will note that right now the code as written has a little bit of an error in it because it says delete P. And delete P says, well, follow out to 32 the address you're at and mark it as available. The next thing I did was said delete Q. Well, Q points to the same place P did. So in fact, I'm saying take that piece of freed memory and mark it freed again. There is no real guarantee about whether that's going to do something sensible or whether it's just going to ignore me. One thing it could do is just say, well, look, that memory's already freed, so you saying to free it twice is kind of stupid. On the other hand, it could still cause some more problems depending on how the heap allocator works. There's no guarantee. So it becomes very incumbent on the programmer to be very careful about this matching, that if you make a new call, you make a delete call. And if you've already made a delete call, you don't make another one accidentally. So I really should have that line out of there. The piece of memory that Q originally pointed to, right, I no longer have any way to get to. And so I have no way of making a delete call to it and freeing it. And so this little piece of memory we call an orphan. He's stranded out there in the heap, no way to get back to it, and C++ will not automatically reclaim it for us. So we have created a little bit of a mess for ourselves. If we did that a lot, right, we could end up clogging our heap filled with these orphans and have to keep getting new memory because the old memory, right, was not being properly reclaimed. We're going to talk more about this. So this is not the all end all of pointers, but just a little bit to think about today. We'll come back on Wednesday, talk more about it, and then talk about how we can use this to build linked lists. And that will be fun times for all.